Hello class, let's learn about some rational expressions, which is section P5 in the textbook. Remember, take notes, write down all the important stuff, rewatch the confusing parts, because that's the beauty of this technology. And if you have anything that's confusing you, a question, something about the video to ask about in class, write it down. It would be a whole lot easier to remember that way. Alright, so P5 is all about rational expressions. So what are they? And it's just a quotient, so quotient means divide, of two polynomials. So we learned about polynomials. When you put one over another, that's a rational expression. Alright, and it's called a rational. Think of rational, the word ratio is in there. It's a ratio of two polynomials. Alright, and it's considered simplified if the numerator and the denominator have no common factors. So it's one of the things that we'll be doing early on in this video, and that's simplifying rational expressions. So here are all the things we'll be doing in rational expressions in this video. We're going to learn how to find the domain and start talking about domain. Simplifying, that's again in the previous slide, it's when all common factors of the numerator and denominator are canceled out. Multiplying and dividing them, adding and subtracting them, and also complex fractions, which are rational expressions inside of rational expressions. It gets pretty crazy, and we'll do that at the end. Alright, so what is the domain? So, a word you may or may not have ever heard of. Hopefully you're somewhat familiar with it, but let's introduce it in this class right now. It's the set of real numbers for which an algebraic expression is defined. So, that poses the question, well, when can an algebraic expression be undefined? And there should be, if there's anything in your mind, instances where an algebraic expression cannot be defined. Two that should come to mind are dividing by 0, right? So, like 4 divided by 2 is defined as 2, or like 10 plus 5 is defined as 15. But 2 divided by 0, division is not defined when dividing by 0. So that's one time when rational expressions will have an undefined answer. Another time will be if you're taking the square root of a negative number. Alright, we haven't learned about imaginary numbers yet, but it's not a real number answer when you take the square root of a negative number. So those are the two cases. So let's investigate them. Now, graphically, one second. So graphically, domain is all of the x values that the graph hits or passes through. So we're going to look at some graphs. And we just talked about, we're looking for algebraic expressions that can be defined or not defined for certain x values. Look for dividing by 0. So that means we're going to take denominators and find any x values which make them 0 and take them out of our domain. And also taking the even root, so I talked about square root, but any even root of a negative number, right? Because that's going to result in a non-real answer. So therefore those x values would not be in your domain. So if there are no x values that lead you to divide by 0, or take an even root of a negative, then we can assume, if there's just an equation and no graph provided, that the domain is all real numbers, alright, for now, until we get into like other things like trigonometric functions and so on and so forth. So, find the domain and look at the graph. So, let's look at the graph first. So, let me pull up this TI Inspire software. So, if you don't have one, I suggest you get one. And when you turn it on, you get brought to this home screen. And we're going to graph. So, we're going to open up a new document and add a graph. So, on the keypad, this f1 of x is like y equals. So, we don't have to do anything there. We're just going to type out our expression in terms of x. If there's any other variable, like if this was variable instead of x was like a or b, then we would still use x on the graph. So I'm going to type this in. So if you hit control division, it creates a blank rational expression for you. So we could type in the numerator, which is just x. So on the bottom of the keypad you just hit x, and then so the cursor is in the denominator now, and we're going to type in this polynomial. Alright, I apologize, sometimes this app pauses for no reason, so I have to pick up where we left off. So this is where we were, typed in the rational expression. So you're just going to hit x, and then hit the caret, and you can get a 3 in the exponent, and then hit plus. You got to hit the right, so you get out of the exponent, or else you might just keep typing in the exponent. Now what I did, I actually pressed down, so I'm in the next functions tab. So if you just hit up, you'll be back to where we were. So you want to make sure the cursor is in the denominator. So I'm going to hit right, and then down, and then right again. So right, if I hit left, I'd be typing in the exponent. So you want to be careful of that. I'm going to hit to the right, and then hit plus. That's right there. 10 x squared, and then plus 24x. Then we hit enter, and we see some domain restrictions, right? What does that mean? Well, certain x values that the graph isn't going to hit. So if we look at the graph at around -4, if we look at as it approaches -4 on the x-axis from the right, it's going to approach infinity. But as it approaches -4 from the left, it's going to approach negative infinity. And what's actually happening here, there's like a little boundary. The graph will never actually hit -4. So when we write the domain of this function, we're going to say that -4 is not part of the domain, because it's an x value that the graph will never hit. Same thing happens here at -6. All right, and that's called an asymptote. An asymptote is a vertical line. It could be horizontal, but a vertical asymptote is a vertical line that the graph gets really close to and approaches either infinity or negative infinity from either side, both sides, and never actually crosses that x value. So two numbers that are not in our domain, two x values, would be -4 and -6. All right, and there's actually another domain restriction here. And if I hit menu, trace, graph trace, I find the other one, 0, undefined. All right, now if you hit to the right, you see like when you plug in 3 into the function, you get 0.016. But when you plug in 0 into the function, you get undefined. And that's because 0 is a 0 of the denominator. It's going to make your denominator 0, thus the entire function is undefined. Just like when you plug in -4 and -6. The difference is when you plug in -4 and -6, -4 and -6 are only zeros of the denominator. Right? The only 0 of the numerator is 0, which is also a 0 of the denominator. So when you have a common factor of the numerator and the denominator, that x value, in this case 0, will not be in your domain, but it won't affect your graph like a -6 or -4, things that are only zeros of the denominator. If it's a 0 of both, then you're going to have what's called a hole, which is what's happening right here at 0, undefined. Right? And if we go over and trace over at -4, see the function jumps, when you're at -3.9, it jumps from a positive number, and then x is equal to -4.2 to a negative number. If we want to get closer to there, we can do menu, trace step. So it traces every whole digit, every whole number. So see, -4 is undefined. When you plug in -5, it is defined as -1, so -5 is in the domain, but -6 is not. All right. So now let's look at how to get that the domain is all real numbers except -6, -4, and 0 without using a graph. Alright, but first I gotta charge my computer, so I'll be right back. So this is how you would find the domain of a rational function algebraically. Alright, I just wanted you to see what the graph looked like first, so what I'm talking about algebraically makes more sense. So what we're gonna do is factor the top and the bottom. So the numerator is just x, so no factoring needs to be done. The denominator, we can pull out an x, because each of these terms has an x in it. Then we're left with x times x squared plus 10x plus 24. Alright, and then that could be factored even more. So you get x plus 6 times x minus 4. Alright, now we're going to learn how to simplify rational expressions in a second, but the first thing you want to do before you simplify and after you factor is find the domain. So after you factor, the zeros of the denominator will be taken out of the domain. So the domain is all real numbers, And then you say x cannot be any zeros in the denominator, which in this case would be 0, -6, and -4. I made a mistake here. This right here should be a plus sign. Alright, so this right here is the domain of this rational expression. Alright, and again, we looked at the graph and we saw that the graph never hit these x values. The graph never crossed x equals 0. It was undefined. There was a hole there, and there were asymptotes at -6 and -4. Now, to simplify, if we were to write this rational expression more simply, you would do that by taking the factored version and canceling out any common factors, because x over x is just going to be 1 over 1. So it's not going to affect the graph, except at that one point where it's undefined, which created that hole. Alright, so that's why it's important to find the domain before canceling out, because you might accidentally put an x value in a domain that's not there. So the final answer of the simplified rational expression would be that, but the domain is still x cannot equal 0, -6, or -4. Alright? Next slide. Alright, the square root of x plus 7. Alright, so not a rational expression, but still, if we're talking about domain, it's worth talking about this square root of x plus 7 because it has domain restrictions. So if we were to go back to our graph, we'll go home, hit the home button, open up a new document, don't worry about saving that, and then go add graph. We can now graph the square root of x plus 7. So to find the square root button, it's right above the x squared. So you could do control x squared. I'm going to get the square root function. Another way to do it is this button next to the 9 has a whole lot of functions in it where, square root, rational expressions, absolute value, degrees, minutes, seconds, matrices. So if you can't find the button on the face of the calculator, often check here. So we don't need that right now. So I'm going to hit escape. Alright, now I want to type in x plus 7 right there. So x plus 7. And we'll notice that the graph starts at -7, and then x just kind of approaches infinity, and y gets bigger and bigger. Alright, that's because for any value less than -7, right, if you plugged in -8 here, f of -8 would give you the square root of -1, which is not a real number, which is why it doesn't appear on this graph. So when you're looking for domains of square root functions, take what's inside the square root and say that has to be positive or negative, because you cannot take the even root of a negative number and get a real number. Alright? So to kind of prove or find the domain without a graph, I'm going to do what I just said. Take what's inside the square root, x plus 7, and say, alright, that has to be positive or 0. Subtract 7 on both sides, and you get x is greater than or equal to -7. That's your domain. Alright, and the graph just kind of shows that by starting at -7 and going to the right. Alright. This is a quadratic. Alright, you're not dividing by 0. You're not taking the square root. So the domain is going to be all real numbers. Alright, it's that simple. This symbol right here is a Greek symbol. Looks like a C with a line in it. That means belongs to. Sorry if I didn't reference that earlier. And then this boldface R is the symbol for real numbers. Alright. And we're going to be using those symbols a lot when talking about domain. Alright, and before, this symbol meant does not equal. So the domain for this one is all real numbers. Any polynomial, like a quadratic here, is going to have a domain of all real numbers. Alright, and if we just quickly graph it, we'll go, without making a new graph, we can just hit tab and then hit the up button, and we can erase what we have here and graph that quadratic. And I actually forgot what it was. X squared plus 3x minus 7. Alright, so x squared plus 3x minus 7. And the graph kind of gets cut off, but we can actually zoom out. So you can do menu, window zoom, zoom out, and place the cursor near like the center of the window that after it's zoomed out, and you could see the more you zoom, the graph is going to eventually hit every x value. Now it looks like it's going up to the right and left, but it is going a little bit to the right and left. So like if you were to keep zooming out, eventually this would hit every x value, slowly, but any polynomial is going to be continuous. It's going to approach infinity and negative infinity on both sides. So the domain's all real numbers. So there's really no x value that the graph is missing. All right. One more domain question is, what if you're dividing by something that has a square root? So this isn't really a rational expression, but it's a good domain question. So first off, we are dividing by the square root of 4x minus 2. So we want to make sure that the square root of 4x minus 2 does not equal 0. Alright, and we also want to make sure that 4x minus 2 is positive. Alright, so this cannot equal 0, but it has to be greater than 0, because if 4x minus 2 is equal to 0, then you're going to be taking the square root of 0, which is okay, but then you'd be dividing by 0. But if it's positive, take the square root of it, divide by it, it'll still be positive. Alright, so first we want to make sure that this square root of 4x minus 2 doesn't equal 0. So we're going to solve this. We're going to square both sides, and we get 4x minus 2 does not equal 0. And then we're going to add 2 and divide by 4. So when you divide by 4, you get x cannot equal 2 over 4, or 1/2. Alright, so x cannot equal 1/2. But we also have to make sure that x, or 4x minus 2, is greater than 0. So we're going to add 2 to both sides, and then divide by 4. So you get x has to be greater than 1/2. Alright, so that kind of got messed up right there. So x has to be greater than 1/2, and it cannot equal 1/2. So, I mean, that's the same thing as just saying x has to be greater than 1/2, but not greater than or equal to. Strictly greater than. Alright, so that would be the domain, because the only thing we have to worry about is dividing by 0. Alright, well, we took 1/2 out of our denominator, and we have to make sure that we are not taking the square root of a negative number. So that's what we did here. We said 4x minus 2 had to be positive. So as long as x is greater than 1/2, then we won't have any domain issues. Alright, so the domain would be x is greater than 1/2. Alright, now that was just domain. So let's talk a little bit about simplifying rational expressions. And actually, sorry, I have to go look at this graph. Let's see what this graph would look like real quick. So let's do, we're going to do control. So let's erase this. We're going to hit tab and up, right? And then do control division. And then we get 12x minus 6 in the numerator. And then the denominator is going to be control x squared, the square root of 4x minus 2. And it doesn't look like much because we're really zoomed out. So if you want to go back to the normal window, you go menu, window zoom, and we could just do back to standard. Alright, and we can see that this graph, it's starting at x is equal to 1/2, and then x is just approaching infinity. Alright, and I bet if we traced it, we would see that it's undefined at x equal to 1/2. So we do trace and then trace step to trace it every 0.5, and then do menu and then trace, undefined, undefined, but then plug in 1, you get an answer, plug in 2, or 1.5, you get an answer, plug in 2, you get a number. Alright, so domain x is greater than 0.5. Alright. Simplifying rational expressions. Rational expression is considered simplified if the numerator and denominator have no common factors. So we do that by factoring the numerator and denominator. Then we find the domain. Then cancel out common factors. Alright? We do not cancel out and then find the domain, because then you might accidentally put numbers in your domain that shouldn't be there. Alright, so factor, find the domain, then cancel. Alright, it's kind of like reverse alphabetical order. F for factor, D for domain, C for cancel. And then bask in the glory of your simplified rational expression. So let's do it. Alright, so step 1, let's factor everything. So factor the top, that's going to be x plus 6 times x minus 2. Alright, because those two numbers multiply negative 12, 6 and negative 2, and add to 4. And then in the denominator, we can pull out a 3. And you're left with 3 times x minus 2. Alright, so we factored. Now, check your domain. So the only numbers that need to be taken out of our domain is 2. So our domain is x does not equal 2. Then we cancel. Cancel that out, and you get x plus 6 over 3, where x cannot equal 2. Alright, so that would be this expression simplified, right there. Final answer. So what does that mean for it to be simplified? It means that if we were to graph this original function, and then graph this function right here, as long as we didn't graph over x is equal to 2, then those two graphs would be identical. Alright? And if you want to just do that right now and see, those two graphs would overlap on each other. They would both have holes at 2 and be undefined at 2, and they look exactly the same. Because the only difference is the first graph had this factor of x minus 2 over x minus 2. But for any value of x, that's going to equal 1, except for 2, where it's going to be undefined, which is why we took it out of the domain. Alright? Here's another one. Let's factor the top and factor the bottom. So we can pull out an x, and we're left with x squared minus 1 in the numerator. And then we can factor that even further, and that's a difference of 2 squares. Alright, so that's going to be the numerator factored. The denominator factored, we can rewrite it as x plus 2 times x minus 1. Alright, so step 1, factor. Then, before we cancel, we're going to exclude certain values from our domain. So x cannot equal negative 2 or 1 because those are the zeros of our denominator. If we plug those numbers in to this original function here, it would be undefined. So we take those numbers out of our domain. Now we cancel. So we cancel x minus 1 over x minus 1, and we're left with x times x plus 1 over x plus 2. Alright, and it's always good to put these in standard form. So if you just distribute that x back in, we get that, where x cannot equal negative 2 or 1. Alright, so that is the simplified version of that. And what does that mean? Their graphs would look exactly the same, except, well, as long as we account for these holes here, as long as we don't graph this bottom simplified version over x equals negative 2 and x equals 1, then the graphs will be exactly the same. So there is no except. They are the same graph. One's just a simpler version of the other algebraically. Alright? Alright, I think I'm going to cut this video off and make a new one for multiplying and dividing. So, thank you for watching, and have an awesome day. And I'll see you in class.